how electricity gets to your home. It starts all the way over here at the power plant. Now in the power plant they have an AC generator. And that's turned typically, maybe if it's a hydroelectric plant, by falling water, or it could be turned by a steam turbine where they burn coal or they burn natural gas, or they have a nuclear reactor which heats water up and boils it into steam, and they use the steam to turn the AC generator. Now the AC generator, it's very easy to produce 3 phases. And they do that. One phase is like this. Then 120 degrees later, they produce another phase. And then because the motor is turning, there's 360 degrees. So another 120 degrees later, they produce another phase. There's your 3 phases. Now, that's why they have 4 lines coming out of the power plant. They have one for each phase, and they have the neutral. Now they come to the power transformer, the step-up transformer. Now we know that the power in the primary has to equal the power in the secondary. That's because of the conservation of energy. Now, if we have power equals current times voltage, if we increase the voltage tremendously in the secondary, the current is reduced proportionally so that we're transmitting the same amount of power. That's kind of like one of the beautiful things about a transformer, is that it does this kind of power conversion where you can step up the voltage, the current is reduced, but the same amount of power is transferred. The AC is transmitted at very high voltage, typically 166 kilovolts or maybe to 700 kilovolts. Now it's transmitted at very high voltage, and that's so that the current is very low. We know that Ohm's law equals current times resistance. If I take this formula and I substitute it into here, we get power equals I squared R. That means that as the current is increased in these transmission lines, the power lost in the resistance of the wire is proportional to the square of the current. So they want to keep that current very low, and they do. That way the power loss in the transmission line, which could be 100 miles long or more, is really minimal. Here are the transmission towers and the overhead transmission lines. Here we have the phase A, the phase B, and C. Now the neutral is up here. You really can't see it, but the neutral wires, they go up here between the towers, and they're really to attract lightning. That way the lightning does not hit any of the phase conductors. The neutral will then ground the lightning through the metal transmission towers to ground. Now these wires are special in their construction. Here's a picture of one of the overhead transmission lines. Now copper would be an excellent conductor, but it's very expensive. So what they do is they use aluminum. Now aluminum is not very strong. So what they have to do, they have to find something to reinforce or give the aluminum some strength. What they do is they form the aluminum into these spiral filaments. They spiral it around the inner core. Now the spiraling is really a mechanical, just to keep the filaments from unwinding. Now the inner core can be different materials. If it's called ACSR, then it's aluminum conductor steel reinforced core. They will have steel filaments. In this picture, it's aluminum conductor with a composite core. And that's what gives the transmission line its strength and its ability to span the distance between the different towers. The physical length of a 60 Hz AC electrical signal is 3,100 miles. Because the AC transmission line is very short compared to the 60 Hz wavelength, losses are kept to a minimum. If the line was 775 miles long, it would act like a quarter wave antenna and the 60 Hz signal would radiate into space. Nikola Tesla selected 60 Hz because he found that the streetlights didn't flicker. Here's the neighborhood electrical substation, and very often the three phases come in, and they come into a transformer, and the neutral, they don't take the neutral right there, they just take the three phases, and this is the primary, and they use what's called a delta winding in the primary. And then in the secondary of the transformer, they use a Y winding or a star. And that in the middle of the star, that's where they generate the neutral that goes to the neighborhoods. Here's some more step-down transformers. So they keep stepping down the voltage. Each time they step down the voltage, they get an increase in available current. Now it's in three phases. Now if you're in a factory, you may get all three phases, but if you're at home, you're only going to get a single phase. Now when it steps down the voltage to say 7200 volt AC, now what happens is it gets to the pole outside your home, and there's the pole transformer, and there it's stepped down to 240 volt AC. Now let's take a closer look at the pole transformer. I'm going to make some measurements now. What I'm going to do is I'm moving one probe here on leg 2 and the other probe on leg 1 because I want to know the voltage between the two legs. And what it comes out to, this is the waveform I get. Now I'm using the green probe right here as my reference point, and I get a nice, this would be 240 volts. Now what I want to do is I want to move the probe to the neutral. What kind of waveform am I going to get? Well, I'm going to get exactly the same waveform. It's going to be in phase, as you can see. They're both in phase, but this time I'm going to be getting 120 volt AC. So we can see that the voltage is in phase. Now let's see what happens when I move the reference points around. Let's say now I move my reference probe to the neutral, and I'm going to measure the voltage between the neutral and leg 1. Well, here it is. This is what I get. I get 120 volts. Now I'm going to move my probe. I'm going to measure the voltage between the neutral and leg 2. And what do I get? I also get 120 volt AC, but look, they're 180 degrees out of phase. Now this whole idea of something being out of phase, that's simply because of where you put your reference point. Now they call this, sometimes they call it phase A and phase B. And they are 180 degrees out of phase, but that's because you're using the neutral as your reference point. If I use either leg as my reference point, then they all appear to be in phase. This would be your house, and on the street you'd see the electrical pole. And on top of the pole is the pole transformer. This is what's going to step down the voltage that's coming in. We have 7200 volts on the primary of this pole transformer, and it's a single phase. It just looks like a regular sine wave coming in. Now the pole transformer has a secondary. The secondary is center tapped, and the center is the neutral, and that goes down to the ground. And it's also, the neutral is carried here in this wire, along with the other secondary, which is the phase A and the phase B. That's 240 volts AC coming into your home. And it goes through comes down here to the electric meter, then it comes up to the service panel. Here the neutral is bonded to another grounding system in the service panel.